So we are starting graphing. We're going to look at the parent functions. The concept of a parent function should not be brand new to you. You've been talking about parent functions since Algebra 1, right? So it is important that you know 3 things about each parent function. What it looks like on the graph, like the basic sketch of it, what the actual equation is, and what the anchor points are. And we'll talk about what anchor points are here in just a second, okay? So we have what's called function families. So a function family is a group of functions with similar characteristics. The parent function is the simplest of the functions in a family. You must be able to recognize each of these functions along with their characteristics, okay? That if you can't do this, it's going to affect more than graphing because it really will help you identify some other things, okay? And most of this you should kind of already know, but there might be a few things where I'm kind of throwing in some extra stuff, okay? So let's look at the linear, the easiest of the parent functions, right? So a linear parent function is just f of x equals x. That's the most basic line there is. That's it. That's what it looks like, okay? We have what are called anchor points, and the anchor points are what we're going to use to actually transform these. So when we do transformations, we're not substituting in a value for x, getting in a value for y, having a bunch of points that we're going to go plot, then plot our points and draw a graph. That's not how you transform things. Transformations are literally taking the parent function and moving it around and stretching it and shrinking it, and you do that using the anchor points. The anchor points are easy. Don't make them harder than they are. It's not something you have to memorize. You can think about what makes the most sense on the graph. Because even without numbers on your graph, I'm going to show you how you're going to, you can plot them and know where they are. There's either 3 or 5, okay? A couple of them have 3, most of them have 5. So for your linear, there's 3. There's one right here. That's at 0, 0. That's true for almost all of them. There's a 0, 0. And then we'll use 1, 1, and negative 1, negative 1. Those are the 3 easiest points on that line, right? So my anchor points then, they are at negative 1, 0, 0, and 1, 1. So when I say you have to sketch your parent function and its anchor points, I would want to see something like this. Notice how I'm not on a grid, I'm not counting points, I'm not making hash marks, and then you can just put your anchor points right here. So what's going to happen is some of you are going to be able to do that on these, but then you're going to be like, I know that much, but I can't figure out where they actually are on the graph. So you think about what makes sense for the function you're doing. If I substitute 0 in for x, I get 0 for y. If I substitute 1 in for x, I get 1 for y. Make sense? And that's how you know it's at 1, 1 and not at 1, 3 or something like that, because that wouldn't make any sense. Okay? So those are your 3 anchor points. For this line, your domain, what's the domain here? What's the smallest x value I can have? Keeps going. See, since this keeps going like this, so the smallest x value I have is negative infinity. And this graph goes all the way then to what? Infinity. Range, what's the smallest y value? Negative infinity. And then that goes to infinity. Okay. My x-intercepts, how many times does it cross the x-axis? Once. And it's right here. That point is 0, 0. And since it says intercept, you write it as an ordered pair. What's my y-intercept? 0, 0. And then, so what I want here, where it says extrema, what I really meant, and I did it wrong, I really meant critical points. So we won't change it on every single one of them, just know that's really what I want, and let's talk about the differences here. So extrema are your maximums, minimums. Your critical points are maximums, minimums, and point of inflection. So critical points includes the point of inflection. So anywhere it says extrema, if there's a point of inflection, we'll include that too. So since this goes to negative infinity and infinity, there are no extrema. There's not a maximum or a minimum, and there's no point of inflection. So on this one, it's none. Increasing and decreasing. To change from increasing to decreasing or vice versa, you have to have a maximum or a minimum. I don't have one. So I'm not changing from increasing to decreasing, which means this function is either increasing the whole time or decreasing the whole time. Which one is it? You can't increase and decrease at the same time. As x goes from left to right, what's happening to your y values? They're increasing. So the function is increasing over the entire domain. So it is negative infinity to infinity. Decreasing would be none. Whew, my board's bouncing for some reason. All right. So then my end behavior, the way we write that, as x approaches infinity, f of x approaches. All right, so as x gets bigger and bigger and bigger, what's happening to y? Where is it going? Infinity. Very good. And then as x approaches negative infinity, f of x approaches. So this is the only time you go from right to left. The only time. Everything else is left to right. As x approaches negative infinity, where are the y values going? Negative infinity. And sorry, I know there's not really, probably running out of room right there. Okay. We good? Are there any discontinuities? No, because I don't have to pick up my pencil the entire time. So there's none. And then we're not going to worry about even or odd. Just don't worry about that. Okay, easy enough? That's a line. And even though we talk about the anchor points, really when we end up graphing the lines sometimes, you have other ways to graph lines, and most of the time that's easier anyway because you already know how to do it and it's fine. Okay, now let's look at the absolute value. All right, absolute value. So the parent function is f of x equals the absolute value of x. My anchor points, if you got a 0, 0, we're going to use a 0, 0. And then you just use 1 on either side of it. So I'll use 1, 1 and negative 1, 1. So again, if I tell you to sketch it, I just expect something like this, nothing beautiful and perfect, and then your anchor points like this. But then you have to know where they go. How do you know where they go? 0, 0 is obvious. Then if I substitute in 1, what do I get out? 1. If I substitute in negative 1, I get 1, right? So this is negative 1, 1, 0, 0, 1, 1. What do you mean, what way? Like if you put this one first? Oh, yeah, I don't care. As long as you get x and y in the right spot, you're good. And you're not going to have to actually write these out other than on here. Like at the other times, you just have to know where they go. But yeah, but no, it's fine. All right, we good on that? So what do we think the domain is here? What's the smallest x value? Negative infinity. My x values, yeah, negative infinity. And I go to infinity. What's my smallest y value? 0. And then it's going to continue to infinity. So do I put from infinity to 0? No. You know why? I go left to right, bottom to top, least to greatest, or you're going to make my head explode. I'm going from bottom to top. I start at 0. 0 is the first y value I come across, right? So I go from 0, and it keeps going. All of the y values all the way to infinity will be used. I never include infinity. Do I include 0? Is 0 a y value? Yes. 0 is something I can plot on there. So that's what that range looks like. Range is the only interval that you put the y values in. And domain and range are the only ones you worry about open and closed also. The rest of them are just all open. Okay. All right, x-intercepts. Easy like the other one, right? I only have 1, 0, 0. Y-intercept is also 0, 0. Do I have any critical points or extrema here? Yes. What would you call this? An absolute minimum. Very good. It's an absolute minimum. So and it's at 0, 0. So that tells me my graph is not increasing or decreasing the entire time. It changes, okay, from one to the other. That's what the minimums do. So where does this graph start increasing? Okay, good, after 0. Technically not at 0, because at 0 is where it's changing, right? So I start increasing here, and then see how my y value is getting bigger, all the way to infinity. So I'm increasing from 0 to infinity. Totally open, because the only thing I worry about open and closed on is domain and range, right? Then it's decreasing starting where? Before 0. So way out here, but remember, we're talking about the y values. The y values are decreasing, but the intervals we write are x. So it starts way out here when x is negative infinity. That's when my graph starts decreasing, and it decreases until we get to 0, because that's where the change is. No question? And we're all good? Any questions? Okay. End behavior. As x approaches infinity, f of x approaches what? As x gets bigger and bigger and bigger, what's happening to y? Bigger and bigger and bigger, infinity. Then, as x approaches negative infinity, f of x approaches what? As x is going to negative infinity, y is going to infinity again. Yes. Okay. Any questions about that? All right, my discontinuities, are there any? Nope, because I can trace the whole thing without picking up my pencil, so there are none, and we're not going to worry about even or odd. Okay. What questions do you have? Good? All right, let's look at quadratic. I'm going to let you try and fill in some of this here in just a second. So quadratic, now you've been doing quadratic since Algebra 1. Your parent function for the quadratic is f of x equals x squared. This is what the graph looks like. It's a parabola, right? So 0, 0 will definitely be an anchor point. And then negative 1, 1, and 1, 1. But that's not enough, because those are the same 3 as we had for the absolute value. And the absolute value, it's just going to go straight out to line. But I need 2 more to kind of help me with the curve. So 1 gives me 1. If I substitute in 2, I'm going to get 4. And if I substitute in negative 2, I'm going to get 4 as well. I didn't make this little table. I didn't make this line long enough, so you can extend it. You're going to need to. So my anchor points are negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. So remember, when you're sketching, and we'll sketch a lot of these together too, but so you would say, okay, this is my parabola. I'm actually going to put my little anchor points on there, and it's just kind of a guesstimate because it's not a real graph, like you're just doing that to get them on there. But then you have to be able to reason through what the ordered pairs actually are so that you'll be able to graph once we start graphing. 0, 0 is obvious. Then 1, 1. So then I always have students say, but I don't know how I'm supposed to know what the other ones are. You think about this right here. So if I substitute in 1, 1 squared is 1. If I substitute in 2, 2 squared is 4. That's how I know what that point is, because it makes sense with that. Okay, we good? All right, so I'm going to give you a minute or two. I want you to fill this in. Okay, you fill that in as best you can, then we'll talk about it. All right, so let's think through this. Daniel, give me the domain. Good. Manuel, give me the range. 0 to negative infinity. Do I include the 0? Yes. Okay. So what you're telling me, 0 to negative infinity? 0 to infinity, right? Positive infinity. Okay. And if it should have been negative infinity, you'd have to go least to greatest, and negative infinity would have to come first, right? Bottom to top. Okay. Good. All right. So my x-intercepts, we're going to say we got 0, 0. Y-intercept is 0, 0. Adrian, do I have any extrema? What is it? Okay, what's it called? Very good. Absolute minimum at 0, 0. All right. Leo, is this increasing anywhere? Yes, very good. From 0 to infinity. Jose, are we decreasing anywhere? Negative infinity, 0. Very good. All right, so then our end behavior. As x, oh, the bouncing, when people walk up there, sometimes the projector bounces and it gives me y'all may not notice it as much, but when I'm up here, it's like, ooh. Okay, as x approaches infinity, f of x approaches what? Y'all tell me. Anybody? Infinity, good. As x gets bigger, y gets bigger, infinity. And then as x approaches negative infinity, f of x approaches infinity. Very good. Any discontinuities? None. And then we are not going to worry about even. Okay. We all good so far? Okay. So stuff you should have already known, and then stuff we've done, which you should be able to figure out by now, right? Let's look at cubic. All right. So cubic here. We actually have we have 5 anchor points here, so that means my little chart is not big enough again. Cubic, this is f of x equals x cubed. 0, 0 is 1. 1, 1, and negative 1, negative 1. Well, those were the same 3 for a line, so I have to have more in order for me to help with the curve, so I know how far it curves out or whatever. So I know that if I have 0, 0, 1 cubed is 1, so then if I substitute in 2, what's 2 cubed? 2 times 2 times 2. 8. And it's off this graph because I was trying not to make the grids way too small on this. So I can't actually plot it on this, but most of the time when we graph, we'll be able to plot it. So it's still an important point. It's just up here off my graph somewhere. And then negative 2, what's negative 2 cubed? Negative 8. So my anchor points then are going to be negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, and 2, 8. So between these two, the cubic and the cube root, which we're about to talk about, these are the ones that the people get mixed up the most. Now, cubic you should have already seen in Algebra 2, at least a little bit. Cube root you may not have. So you know that the cubic looks like this, right? Then we put our little anchor points on there, and you know it's going to look something like this. And then when you have to think, what are they? Because again, you can write this out, but you don't have to write this out every single time. 0, 0, 1, 1. Those are easy. Then when you're trying to remember what this one is, it's 2. 2 cubed is 8. That's how you know what the number is. Okay? We good? All right, you fill out the little chart. Adrian, give me the domain. Good. How do I write that in interval notation? Okay, good. So it is all real numbers, but when interval notation, got that. Okay, good. And then, Adrian, what's my range? Very good. Okay, good. And then same x and y intercept, right? 0, 0, 0, 0. This is pretty basic. All right, extrema, or really critical points. Leo, do I have any? What's it called? Do you remember? Okay, but you know there's something there, so that's good. That's something. So can anybody? So he's right. There's a critical point at 0, 0. Anybody remember what it's called? It's where it does the little wiggle. It's a point of inflection. There we go. All right, so this extrema is really, I can't even write correctly. I'm going to put CP for critical points. So there is a point of inflection at 0, 0. Okay, so remember, the only time I change from increasing to decreasing is if I have a maximum or a minimum. The point of inflection changes the shape, but it doesn't change the direction. So that means that this graph is either increasing the whole time or decreasing the whole time. Manuel, which one is it? Am I increasing the whole time or decreasing? Increasing, because from left to right, it's getting bigger, right? So I'm increasing from negative infinity to infinity. So I'm decreasing none then. So remember, if I'm increasing, so I'm increasing kind of quickly, all I'm doing is I'm slowing down and then I speed up again. That's what's happening. Okay. My end behavior, as x approaches infinity, f of x approaches what, Daniel? Infinity. And then as x approaches infinity, f of x approaches what, Jose? What? That's okay. As x approaches, I put infinity again. That's why you were, what? Why? You asked me, it was a trick question. Now, as x approaches negative infinity, f of x approaches negative infinity. Very good. Are there any discontinuities? No. And then we don't care about even or odd. Okay. We all good on that one? All right, so now let's look at the next one's the square root. I'm sorry, you're not going to get this one mixed up with the square root. The cube root is the one that's most likely new to you. So let's look at the square root first. I wasn't paying attention to what was next. Square root function, f of x equals the square root of x. That's why it's called the square root function. Here I have 3 anchor points. I don't need any more than that. 0, 0 is still one of them. 1, 1 is still one of them. Now, for the other ones, I've substituted in 2. Well, if I use 2, that's going to give me the square root of 2. That's yucky. I don't want that. What's the next x value I can put in to get a decent y value out? 4. So 4, 2 is your third one. Okay, so we have 0, 0, 1, 1, 4, 2. Don't get it backwards with the 2, 4. All right. So again, here's your thought process when you're trying to come up with them. Some people will just know them, like you just memorize them, they make sense. Other people, you have to figure them out every time. That's fine. It's not that big of a deal. So if you know it looks like this, okay, you got that snapshot picture in your mind. 0, 0, beautiful. 1, 1, still. But then you think, okay, well, it's not 2. So you ask yourself what I just asked you. What's the next decent number I can substitute in to get a decent y value? That's how you know it's 4, 2. Make sense? That's how you're going to come up with that. All right, you fill in the chart. You haven't even written anything down yet. I'm going to make you give me all the answers. What are you doing over here? Okay, Manuel. What's the domain? 0 to infinity. Do I include the 0? Very good. What's the range? Very good. Do I include the 0? Yes. Very good. Okay, good job. All right, so then my x and y intercept, it's the same as it has been in all of them. They're actually all of these parent functions. We have the exact same one. Adrian, do I have any critical points or extrema? Yeah. What do I have? Very good. I got an absolute minimum at 0, 0. All right. So absolute minimum is where I can change from increasing to decreasing. But given where that absolute minimum is, there's nothing to change from, right? Which means that it doesn't change. So it's either increasing the whole time or decreasing the whole time. Leo, which one is it? Increasing. So what would my interval look like? Very good. And then I'm decreasing none. All right. So then let's look at our end behavior. As x approaches infinity, f of x approaches what, Daniel? Or anybody? Infinity? Okay. Okay, now the second part's going to look different because usually second time, unless I mess up like the last one, it's as x approaches negative infinity. Does x actually approach negative infinity? No, it ends before that. X is only going to go to 0. So I'm going to say as x approaches 0, f of x, what is f of x approaching? 0. Okay. So since it's in behavior, it's wherever the end is. And for a lot of what we're doing, it's infinity, but sometimes it's not. And I know we actually get there, but there's still a lot of times where we're only concerned about what happens as we approach it. We don't really care if we actually get there or not. But x is approaching 0, so is y. Okay, we good? Is this continuous? Or, I'm sorry, are there any discontinuities? Let me ask it the same way. No, so there's none, and then we don't care about even or odd. All right, we good? Any questions at this point? All right, so let's look at the cube root. So this one's probably new. I think the graph is, you've done cube roots, you should have anyway. So cube root function, f of x, is equal to the cube root of x. All right? So I'm going to have, again, definitely these 3 anchor points. But those are the same 3 as I had for a line. And again, I need to get my curve correct. So I know if I substitute in 1, the cube root of 1 is 1. If I substitute in 2, the cube root of 2 is yucky. I don't want that. What's the next number I can put in to get a decent y value out? So think about it backwards first, meaning that I know that 1 cubed is 1. What is 2 cubed? 2 times 2 times 2? 8. So since 2 cubed is 8, the next thing that will get me a pretty y value would be substituting in 8 so I could get 2 out. Does that make sense? So the thing is with this and the cubic, if you look back up at the top of your paper, these are very similar and the numbers are similar because they're just inverses of each other. So it's kind of easy to get them mixed up in your brain. So make sure you know if it's standing up or laying down, and that'll help you get the 2 and the 8 in the right spot. Okay? So, and again, this is off my graph. And same thing, I'd have negative 8, negative 2. So my anchor points then look like this. Negative 8, negative 2, negative 1, 0, 0, 1, 1, 8, 2. So the 2 and the 8 are backwards from what they were in the cubic. That's why having the picture in your mind and being able to sketch it, oh, that's really bad. And they don't have to be beautiful, but I was trying to at least hit the, it's not an art class, but you need to have just the general idea. So if you can graph that, if you can draw that, and then you say, okay, here are my anchor points, I know they're like this. then if you try and use 2,8, does 2,8 even make sense from my bad little graph? It makes no sense because 2,8 would be right here, right? This would have to be 8,2. So if you know it's laying down, you can get them in the right order. So that's very important to be able to think through that. Okay, we good? All right, I'm going to give you a couple minutes to go ahead and fill this out. All right, Jose, what's the domain? Good, negative infinity to infinity. What's the range? Very good. All right, so then my x and y intercept, again, 0, 0. It's literally the same for every single one of those. Do I have any critical points, Adrian? Yes. What do I have and where? Okay, and what's it called? Very good. Point of inflection at 0, 0. So there's no maximums or minimums, which means I am either increasing the whole time or decreasing. Daniel, which one is it? Increasing. So I'm increasing from negative infinity to infinity. I'm not decreasing at all. Then my end behavior. As x approaches infinity, f of x approaches what, Leo? Infinity. Very good. And then as x approaches negative infinity, f of x approaches what, Manuel? Huh? As x approaches negative infinity, what does f of x approach? Negative infinity. Very good. Are there any discontinuities anywhere? No. And we don't care about even and odd. Okay. Any questions at all? All right, so do you have to have all of this memorized? No, because this stuff, just by what you know how to do, you can figure out really easily, right? Do you have to have the anchor points memorized? No, you have to have the picture in your mind, and then you will be able to figure these out if you don't just block that in your mind. It's not that big of a deal, really. Okay, we good? So your assignment today, super easy, okay? It's in Delta Math. There's like, and I think the way I put them in, it probably looks like there's like 10 sections. There's not, there probably is 10 sections, but there's literally one question in each section. I think when I put them in like that, like I can't, that's like, it's the only way I can do it. So you have 8 minutes. I bet you if you got in there, you could probably get it done.